let me do it one more time. So I will kind of just quickly go here. So in this lecture, we going through the task 16 review. We organized the work based on the tasks which came before it, and we have a special logic of the game which was forcing us to do certain patterns in the code, and the passable and unpassable pathways were kind of depicted on the map. So I just talked about this organization of the 5 files, and that each of them was logically self-contained to contain the behaviors and the definitions of what it needs to do and what it needs to represent. And one which was not dependent on anything else was world RS, because it kind of defined the world, it defined the map, it defined the constraints, but it was not in itself depending on anything else. And then the other modules were kind of depending on some of the other modules. The only one which was kind of touching a lot of modules and also touching I/O was the main RS. All right, so then when we code and we keep in mind that it's the main RS which is using standard input output, and the I/O is sort of isolated to main RS only, and we doing some things and we injecting, for example, print line, that violates the boundary of the modules, right? Because we are kind of in the, like, this is inside the Go function, and I just brought it here. So in the game RS, we have the game state, and the game state has it has the Go function, and this Go function we are sort of filling in here. So we kind of need to bear in mind that picture, that game doesn't do any I/O and doesn't do any presentation. Those modules are responsible for presentation and for standard input output, and game is only responsible for the logic, right? So that means if we do something like this, we making kind of a violation of the boundary between the modules, and we should not do that. And also there is a uh, type error. So if we say return, that's not gonna compile because this Go function requires a game result. So in our mental model, we kind of remember that whatever Go does, it has to return a game result. It cannot just return nothing. So if there is a bare return, it's not gonna compile. Okay, so then we have um, a logic error. So we say if we have a border and the border is a river, and we have the canoe, then we quit, which is the reverse, right? There should be and we don't have the canoe, right? So this is like it will compile, and this line will compile at least. But there is like a logic error here because it's missing the negation. And also we're doing the same error as there. We're mixing the IO um, with the module, with the game module, which should not touch IO. And then the final one is we have a kind of current area of where we are, but next area is the option. All right. So this assignment will also not compile because we are trying to assign an optional area to the area type. And that's a common pattern. Like we have area in the box, but here we have area without the box, and we cannot make this assignment. We have to unpack the box. And that causes students some headaches of like how we doing this. And we usually do some pattern matching to extract the values out of the boxes and then manipulate them. So that's what we've been doing in Haskell, and that's what we have to do in Rust as well. So this is just a code snippet, like made up. It is actually inspired by some of the code which was submitted, which was not compiling. And I just kind of highlight why it is not compiling. And when you working on the code, that kind of demonstrates a slightly wrong mental model because we should remember the boundaries of the modules. So in game, we don't touch IO and we don't communicate directly with the user. That's what render and main RS are for. And here we operate on types, and we have to remember what types we are working with and what we should return. And this is what should happen here, right? All right, so question. Which module may call print line? Well, should game be able to use print line? It owns its state, it knows what it is, so it should be able to do that, or no, we should only contain it to main RS and render. Yeah, we should do B, right? We should not mix, we should not cross the logical boundaries of what is the design. And the design is clear. The design is clear that those two are responsible for IO and communicating with the user, and game is responsible for business logic and for managing the game state. It does not directly talk to the user. It is, done here. What happens if we violate the boundaries? Well, the code becomes messy, and then over time it's harder to maintain, and it's harder to make it correct, and we get into problems. So compiler will not stop you. It is something that we have to work on, and we have to kind of make it such that it is consistent and stable. AIs don't really do that neither. So AIs initially, when they generating your initial code, may be quite strict and they may follow this because you told them to follow this. But as they maintain your code, they will put stuff all over the place, and you have to make sure that the AIs that you're working with kind of maintain the logic that you want to be maintained. So that's the sort of the first quick lesson. Modular architecture, organizing things in a logical and consistent way, and then sticking to module boundaries. We will come back to this when we talk about tests, okay? So abstract data types, fun. This is super fun, but you kind of, in the exam, you are expected to use a little bit of proper vocabulary, and I will drill you on some of the notions and vocabulary that we mastered in Haskell. So ADTs, algebraic data types, are kind of a fancy way of saying we have structs and we have enums. Nothing more than that. When you were studying C++, you were mostly focused on product types, on structs and objects. But when we dived into Haskell, we had those data types, which were those or, that something is playing or something is won. It is a little bit similar to union in C, but not kind of like exactly the same. So a product type has fields, and those fields for a particular instance are always filled in. So you have multiple elements. So if you read the book, the Haskell book, you kind of hopefully understood the product types, but the idea is that they multiply. If I have a domain with two items, so I have some sort of bool, and it can have true or false, and I have another bool which might be true or false. Then suddenly I have a data type which can capture four possibilities because each of the fields kind of multiply the domain. So if the domain is Boolean and it has count of two, then if I have two fields like this, then suddenly my domain is of count of like complexity of four, because I can have all possible combinations, right? But if I have a sum type where I have yeah, two is not the best example because 2 plus 2 is also 4 and 2 times 2 is also 4. So, but in sum type, we don't multiply the domains, we sum them. So if I have an item which has of it's a singleton, and then I have a Boolean which have two, then I have three possible state because I have the singleton, and then I have the two states from the from the Boolean. So I would have state of 3. But if I am in the product type and I have an item which has a singleton, it's always the same. And then I have two bools, then I multiply. So then I would have two, only two. So product types, they kind of multiply the domains, and some types you add the domains. Practice that because there will be questions in the exam about product types and sum types, and you should be able to kind of recognize what is what and what the size of the domains are. So that helps with mental models, and that helps with planning how we dealing with the data representations. Intuitions are pretty straightforward. You already have lots of intuitions about structs. So now you just have to get a little bit more into using enums and using the data types, the ones which have which are sum types, right? So in our case, we have a game state, which is a sum type, and we have the playing state, which is a product type. And the product type has some fields, and they are kind of specified here. And then the same as with the data type, with the sum type, we have some variants. So we have a playing variant and we have a one variant, and the playing variant has a context. It has certain value associated with it, whereas the one value does not have it, right? Fluently using both is a little bit hard because you were so far used to that one only, and you have to get your head more about using the sum types. They are super useful. So side by side, Haskell, if we have a border and it's free, river, ocean, mountain, edge. And here we have a public border, which is free, river, ocean, mountain, edge. That's kind of, pretty much the same. The only difference is with deriving. For Haskell, it's a bit simpler. We say, yeah, we can compare them. So there is an equality check, and we can print them. So there is a kind of a converter to strings. And here we do a little bit differently. We say, yeah, we can print them for debug purposes. And we have the partial equality and equality. We have both. And then we have clone and copy. So those are two different ways of dealing with memory management. So let's see, what is copy for? So what do you think copy is? So if you're coming from C++, that should be intuitive to you. We have two things. We have a copy semantics and we have a move semantics. The copy semantics makes actually a copy, so bit by bit copy. And then a move semantics kind of reallocates stuff, disposes old stuff, and moves the content to the new stuff, right? So deriving, like in Rust, deriving copy means you're not introducing move semantics. You're just making sure that the copy is like copying is by value, not by move. It gets a little bit like interesting with the way the memory is managed, and like if you're programming in Rust, you have to go back to your sort of C++ knowledge and remember that we have those two different ways of dealing with making copies of types of instances of types. So then we have other examples where we have payload. So as I said, like one is a variant of the game state, but doesn't have any payload. And then playing has a variant, which is playing state. And playing state is a struct. So if you go to the code, you will see that playing type is just a struct. So it expands our capabilities of dealing with sum types because we can carry a certain payload and then make it much more usable for us. So here we have game event, moved, took, dropped, and narrative. and then each of them has a certain payload, and it's equivalent in Rust. As you can see, they pretty much identical. The only small difference is the syntax, how you write it. So there is less decorations here. Like you just have the variants with the bang, and here you have more like noise, syntactic noise. So that, but semantically they are exactly the same. So here we have a game event with the variants and with the payload. And the question is it a sum type or is it a product type? What do you think? Yeah, you can put your thinking in chat. So is this a sum type or a product type? It's yeah, come on, anyone. Just guess. You have 50% chance of guessing right. Right. Yeah, it kind of looks like a product type because it has area and item and another item and narrative, right? It has all those payloads. So it really looks like a struct, but there is a big difference. If it was a struct, it would be a product type and it would contain all those things in a single instance, which would make it a product type. But because it's an enum, that means at a given instance, you only have one. You don't have area and item and narrative. You only have either area or this item or this item or this narrative, right? So if you say or, that means it's a sum type. If you say and, that means it's a product type. So in this particular case, this is a sum type because it has enum here, and we don't have all those area, item narrative at the same time. We have or. So we have area or item or narrative. If it was a struct, we would have area and item and narrative, right? So, I mean, the simple heuristic here is to check, okay, is it an enum? Then it's very likely sum type. If it's a struct, it's very likely product type. Most like would just be that heuristic will work. All right, so then we have other ADTs, which you are familiar with, maybes and either, an option and a result. They are basically the same. Those are sum types, and they kind of represent error situations and happy and unhappy paths, or some optional values. So sometimes we have no value, so then we return nothing or none, or sometimes we have something and we return that. So we already talked about it, and we sort of use this. In the game, we using optional areas because we want to represent the movements. And if we had this map and we were saying, yeah, you can move somewhere. So if I move from here south, I will have a new area. And sometimes there is an area, but sometimes there is nothing, right? So we would like to have this sort of mechanism for yeah, we talked about this for representing optional areas that there either is area or not. And then for result, we have this game event leading to an error, right? So we either like we are doing something and we even either have a game event or we have a error. So it's the error situation or the event. And here we have the event or the error situation. So it's pretty much the same. So if we ask for the neighbor of an area in a particular direction, we cannot return the area because sometimes there is nothing. So we basically return an optional area, right? And that means if we want to check if we are at the edge of the world, we have to prevent certain things to happen. And then if we are not at the edge of the world, we can do stuff. So if we are at the area and we are checking what the next area is, so let's say we moved south from a particular area, and then we have a next area. So then we have to distract it and check, okay, are we outside of the edge or not? If this is none, this pattern matching will not pass, right? This is a very common pattern in Rust. It's a little bit confusing to people who starting with Rust because of this shadowing. Personally, I don't like the shadowing rule. In programming languages, shadowing means you can declare a new variable of exactly the same name, and it means new things now because you shadow the one which you just shadowed. It makes code somewhat confusing to read because we have next area twice and your brain has to process it, like has to decouple it into two different slots. So next area here means option. This is an option. And next area here means the value of the option if it exists. So if there is some area, then this one will be of type area. This one is type area. This one is type option area. And you sort of need to decompose it in your brain. And some languages don't have shadowing, and I wish Rust didn't have shadowing. Haskell doesn't have shadowing, and it's so much easier to read and process in your head. Rust has shadowing, and that makes it easier to write because you don't need to introduce a new variable, but it makes it harder to read and comprehend. But anyway, this let pattern is very common. What it means is on the right-hand side, you have a concrete instance, concrete variable. And then on the left-hand side, you're doing destructuring. It's like destructuring is a way of assigning value to variables in a kind of a pattern matching way. So here we extracting the area. And if it exists, we do nothing because we don't have any block here. But then else, if that one failed, that means that one is none. And if that one is none, we throwing an error. We could just say if next area is none, we do this, right? But it's a little bit more idiomatic to extract what the value is because we usually want to do something with it. Not in this particular case, but we may do something with the area here, right? So from here, next area is of area type, and we can use it, and it exists, and we can deal with it. This is just a kind of an error check. Not necessary error, but the unhappy path check that the area does not exist and it's none. Do you get it? This pattern, super common. Like you really need to use that pattern a lot. So this let else option is idiomatic in Rust, and it's like something that you will see in Rust code a lot. All right. So then we have pattern matching. So we also have the match pattern matching, where we specify a variable here and we match it to particular instance. And we're doing the same here through pattern matching on the function. So we say, okay, well, there is a render border and it takes a border, and then we just pattern match on the border by doing this. Very similar to the match command. There is a match command on Haskell as well, and you can match inside the body on the parameter which is passed here. But if you can avoid this, if you can do this on the function level, this is preferred because it's kind of easier to read. And it's not embedded inside the function body, it's sort of on the outside already. In Rust, we don't have that. We don't have this ability to pattern match on the function. We have to pattern match on the variable. So we have to use this variant, right? So then if we also have an edge, So if there is a border which is a free river, ocean, mountain edge, then both will have a compiler error. The compiler is our friend, and the compiler will complain that, oh yeah, you're not doing exhaustive search, right? Exhaustive pattern matching. Great. So what will happen if we have this sum type and we added lava, right? So what will happen if we forget to update render error? Well, what will happen is compiler error. And that's the strength of modeling things using types. Suddenly the compiler catches all the places in the code which needs to be checked and which needs to be updated. If you modeled borders as text, and if you have like free river, ocean, mountain edge as text, and then you've added extra variant as text, the compiler cannot help you, and the compiler will be blind to your code changes. And then the errors will be panics at the execution time, at runtime. But because you modeled everything as types, then the compiler benefits from it and makes sure that your logic is updated if you're introducing something or if you're changing something, like if you deleted one of the variants. Then the compiler will complain at every place where you're dealing with the border, right? This is super important, and this is like relevant for designing the model of your domain, how you model what you're dealing with. And the more you're using your types to your advantage, the better it is. The less you're using your types, you're using some hash tables, strings, numbers for modeling your data, then that you cannot take advantage of the compiler and you're doing stuff, you're doing things in a little bit wrong way. So you should always try to think, especially if you're programming in Haskell or Rust, to take advantage of the compiler and of the domain that you're modeling through types. So one small thing that was in one of the students, or was it in the students or in the default specification, was that we have to deal with the we rendering what the took variants are, and we say if you took an axe, we say you pick up an axe. If you took a rope, you say you pick up the rope. And you can see that there is this text which is repeated all over, right? And the only thing which has changed is this thing here. And this thing is a parameter to this. So we can recognize, okay, we should follow a simplification, and we should wrap it up in such a way that it's just one function. Instead of four functions, we just have one function because it always takes the parameter, which is whatever we want to render, and then the beginning is the same for all of them. So we don't need four functions, we just need one, which covers, the item, and then you can format what you display based on the content of this item, right? Do you see it? So this is a small code smell. You would say, yeah, this is a little bit, yeah, smelly. It kind of looks, we are repeating stuff unnecessary, and we can wrap it up into a single function instead of four functions. You should do that, right? This code smell is not good. You should change it to a single function. And the main reason why is if we add shield. So if we have this, those are called arms. We have four arms, four branches, and then here we just have one, right? So if we have just generic branch, generic arm, or if we have per item, right? And we adding a shield. So if we have per item, the compiler forces us to handle the variant explicitly, right? But if we have a generic one, it will suddenly work automatically because this is kind of a generic function. So this function generically takes any item and produces the desired output in a way that does not need an update. If we introduce a new item type, we don't need to touch this function at all, right? So this is an added advantage to be programming generically, because suddenly the changes are more localized. The only change will be into the item type, but the display function will sort of automatically work, right? Especially if your behavior is same as here, is very generic. Do you see it? That why this is a code smell? I hope you do. All right, you will have to be able to identify code smells and small improvements into the code, which is using type systems in the exam as well. Okay, so then the let me check the time. Yeah, let's do state machine as well. So in the game, the game state was modeled as a sum type, as a data type, with two variants, playing and won, right? And the game starts with the game state being playing, and then at some point the game changes to won, and then there is a victory, right? So if you get to the winning condition and you're interacting with Casey, with the Casey variant, Casey arm, then you have to change the state of the game to won, and then you're saying, yeah, there is a victory, right? So then this dereferences the game state and modifies the value in place, and then the old playing state is dropped. There is no playing state anymore, right? So this variant is gone, and then we are in this variant now. So if the player access the game state, the global game state, then they will see one. That's pretty straightforward. So then if we have this check, if we're checking if the is game over based on the reference to the game state. So after this call, what will the function return? It's a variant A, because the value of the variant is the state. There is no extra thing. There is no separate Boolean field or anything that you need to check. This in itself is the state, right? So is option A. So what we could have done is we could have a game state, which is like, if you look at this, we have this playing state, which contains all the game state. Oh, like, okay, so this is a game state. And then the game state, when you're playing the game, needs to contain who is the player, where the player is, what is the inventory of the player, what are the items in the area the player is currently in. No, actually, this one is the entire map of what are the inventory items of the various elements on the map, whether the canoe is already ready, and whether the game finished or not, right? So those four we have to keep, and we are keeping them in the playing state. We are keeping them here. And we calling this a game state because when we playing the game, we keeping all those four here. We don't keeping the fifth one because we keeping this one instead with this model, right? But what about this model? We keeping all those four as before, but now directly in game state. And then we have just an extra bool saying, oh, is the game over or not? Could we do that? Could we model our game state this way instead of this way? What do you think? Could you do a game state like this instead? Anybody? So we have to model the state of the game. We have to keep track of all those things. And in addition, we also keep track of whether we just won the game or is the game still on. Yes, that's true. We could. The answer is that we could, but using the bool would be more annoying because we have to sprinkle the if statements everywhere to check, okay, are we still playing the game or not? Instead, we're doing this pattern matching on the game state with this variant where we are basically saying if we won, we don't need all those other fields. And we, instead of doing the if statement, we're doing this pattern matching, right? So we could do this and it would be fine, but it has kind of an annoying effect. One annoying effect is we have to sprinkle everywhere if statements to check if we are still playing the game or not. But you say, yeah, but if statements are not too bad because in the other case, we have to sprinkle those pattern matching things as well, right? But when you sprinkle if statements, you're mixing the happy and unhappy path. Whereas if you're using pattern matching, you have the happy path, which is clean, and unhappy path, which is isolated. You don't have those if statements, right? And second reason is, even if the game is over, you still have all those four fields. So even if this one is true, you have all those fields here. Is the player is in the particular area, and then player has a particular inventory, and it does not make sense anymore. That should not exist. If the game is over, the state of the game should not exist anymore, right? But it does because you combine them together. You combine the fact that the game is over with when the game wasn't over, you had a particular state about the game, and that may or may not be desirable. Like it is pretty much undesirable that you have something stale when the game is over, right? That does not exist when the game is over. So that's exactly what this one's saying. If the game is finished, the playing state does not exist. This one doesn't have any payload. It means, yep, the game is over. There is no player in a middle cave because the game is over. That it makes no sense to talk about the player being somewhere in the game. Um, so you could do this, but it would be a code smell again. It would make the code not communicate exactly what the game is about and that the state of the game does not exist once the game is over, right? So yeah, exactly. So that basically talks about that you would have to do check at every top of the method, which is dealing with the um, of the methods, but player area, inventory, and so on will still exist and accessible in the struct, right? And that is undesirable property. All right, so then what would happen if we add the lost state and carries like a death message? So you lost the game and there is a particular message that communicates to you that, you know, the game is over because you've lost it in a certain way, right? So then it's very easy. You just add it to the enum. And then if you have this is over match, you say, okay, we either won or we lost, right? And it communicates the intent very cleanly. And all our previous pattern matching on the playing state still works fine because it picks up all this state of the game. And then all the existing match on game state that does not cover lost will become a compiler error. So the compiler will tell you every time you're doing a matching, you're dealing with the won and playing states, but now the compiler will say, hey, you kind of lose, you didn't deal with the lost case, and you have to fix all those compiler errors, right? And then you don't need any manual audit. The compiler is your friend, and the compiler fixes things for you. I mean, you have to fix it, but the compiler tells you what to fix, right? If you forgot this in renderer for rendering the game state, it is a compiler error, right? This does not happen in our case because we are doing this type enforcement, and we modeling everything through types, then this extra state in our type system forces the compiler error. So it's option A. So then, all right, so let me have a short break. So we were dealing with this game state representation, and the payload was embedded into the playing state, but not into the winning or losing state. In losing state, we have a certain payload which communicates to the user why they lost. When we are playing, we have to keep track of the game. And then if we won, like that's it. And then everything is very enforced by the compiler, right? We could do this way, and then we could say extra thing about like losing or whatever and communicate it here, but then we are combining too many things. We kind of making a spaghetti code, because then this does not represent a kind of really a game state. It's an amalgamation of game state, the actual state when we are playing the game, and the state when the game is over, and so on. It's like too messy, right? And it can get messy quite quickly, and it gets annoying to in maintenance. And then if you model things even worse as strings or something, then you getting yourself into the runtime errors. You getting yourself into those silently producing errors when you're actually playing the game. So you should definitely avoid it. All right, so then we talk about the guard. I will make a break and then we come back to this. This one is a little bit more interesting than the state. The state is just like do it always like this. It's always better than doing it like this. Okay. But with guards, it's not such a clean story. So let's have a break. 10 minutes and we come back to the more elaborate example. All right. Welcome back. All right, so what we do is we are now looking into this method, and this method is having this guard, which so from the game we getting the game state, right? So we are kind of in the game state. This is the implementation. Take is inside the game state kind of implementation. And we have the function take. And basically what we're doing is we're taking the element from the area and putting it into inventory. But we can only do that when we're still playing the game. And to do this check, we also have to extract this playing state, the state, because we will need the state. Let me just go here. This one, all right? We need to extract this one. Because just knowing that we're playing is not enough. We have to know the actual state of the game, like where the player is, what is the map, what items different areas have, and so on, because the player can pick up an item from one area and drop it into another area, right? So we need to know the playing state. So because of that, we need to extract the state from the game state. So we're doing this guard. And now the question is it kind of the best we can do? Can we do it in a cleaner way? So if we go here, the question is that every public method which deals with the state of the game opens with this guard, right? So then playing mute gives us the mutable playing state, which is the inside of the gives us the state of the game, and then we can extract the playing state from it. And then we have this let else, and if we have else, we basically saying, yeah, we cannot do any take or do anything anymore because the game is already over. So there is no game behavior. But if this is true, then we can access the state. And the state is a mutable playing state. It's exactly the one which we have here, right? Make sense? I hope it makes sense. So the question is, we have to repeat it in every method, right? And then is it something we can do? Like, what can we do with this? So we have okay, so if we go here, we have the game state, and inside the game state we have those two variants. We don't have the lost, but we have those two variants. And then inside the first variant, we have the playing state. And the playing state is this struct, right? Here. So playing state is this struct, which kind of contains the actual state of the game. Once you implemented it, this not becomes that code because you are dealing with Canoe. But can we implement this logic on this one instead of the game state itself, instead of this one? What would change? What would change if this like if we move the take? So currently we have the function take on the game state, and then if the game is finished, the function take does not make sense, right? The function, where is the function take here? So we have go and take. If we move go and take from game state and implement go and take into the playing state instead, into this one, that means when we're doing something with game state, we don't have to be checking whether we can do go and take, because that behavior is kind of wrapped inside the playing state. Do you kind of get it? So currently, we have go and take operating on the game state, and game state it has two variants, and one of the variants has the playing state, the state of the game, which does not make sense for when the game is won. But the public methods on the game state always have this guard. Always check, okay, does it make sense to do take? Or does it make sense to make go? Because we can be either in one of the variants. If we move those methods inside the playing state, and we implement the function go and take on the playing state, then inside this function, we don't have to do any guard anymore, because that is the playing state. Like, that function operates on the playing state directly. So it has to be the one which makes sense, right? Would that be very, like, can we do this? Can we move the go and take functions and other functions which operate only on the playing state and throw errors like this behavior, this throwing errors, like you're trying to do take on a game state and the game state does not make sense anymore. So then we have this guard, and this guard always throws an error. It says, yeah, the game is over. You can't do take, or you cannot do go. But if we move those take and go functions inside the playing state into here, then we don't need that guard in those functions, because those functions are just like, just behavior. There is no guard needed, right? Can we do this? What do you think? Yeah, this one is a little bit like, maybe you have to think a little bit about it. So let me show you. Let me show you this. So can I make heck is playing a type? Is playing or won or lost a type? Is it a type? No, those are not types. Yeah, answer. Someone is listening. All right. Playing state is its own struct. Should be able to use it in yes. So Nick has a good intuition. So because playing state is its own struct, then yes, you can do this. You can do this. You can do this. That's correct. Nick is fine. Nick is correct. The question now is, can I have my own implementation on playing, won, or lost? Can I do that? No, I can't, because playing, won, or lost are not types. Those are kind of type instances of the game state. Game state is a type, and playing state is a type, but playing in Rust language is called a variant. And those are not types. So I cannot say implement me stuff for playing. No, you cannot do that. But implement me stuff for playing state, yes, you can, right? So for this, you can. For the variant, you cannot. So that's why this one, this one uh, on inner struct types of enums is a little bit confusing, because it is true, like you can, but not on those, on this you cannot, but on this you can. So neg intuition is perfect. The answer is correct. Yes, we can do this. So we can do this. So yes, it's a valid design. And then the guards move to the call side. Like, instead of them being on the game state level, you basically have to move the guarding somewhere which deals with the game state, because now if you are in the playing state and you extracted the playing state, then you can call take or go on that playing state, but you cannot call those functions on the game state, right? So game state itself does not have the does not have this dispatch. The dispatch is, um, yeah, it's like, let me show you. So we have the playing state. If we move the methods here, if we implement them on here, we kind of did the implementation inside. The game state is like agnostic to it. And then whoever is dealing with game state has to have some sort of dispatch, because you cannot call go on the game state. You have to call go on the playing state. So that means for here, the answer is yes, it's a valid design. But oh, no, no, no. But this one has, like, it's not avoiding the guards, it's moving the guards into a different place. And then if you think about it, every time you're dealing with game state and you have to do dispatch there, your code inside your main RS or render RS will become more convoluted, because every time you kind of you have to do something, you have to do the dispatch over there. So it is possible you can do that, you can do this, and it would work. It would just migrate the dispatch to a different call place, and then it's up to you to decide which one feels better. I'm not saying this model where we have the playing state implementing go take is worse. It's just different. And there is no clear answer. There is no clear winner, whether this model is inferior or superior to the one where those functions sit in the game state. I opted for the methods to live in the game state and have the guards on that level, because to me, to my conceptual thinking about this, that made sense. But you may disagree with this, and you may feel like doing it this way is better, and then migrating the dispatch into the calling side, or which are dealing with game state, is actually more natural for your conceptualization or for the case that you're dealing with. So to cut the long story short, it is not about doing one or the other. I mean, it is about doing one or the other, but the rationale is not that always one wins over the other. Sometimes putting it inside works better, and sometimes doing it kind of in the middle works better. I felt doing it kind of in the middle. Yes, I have to put this guard into those methods, but there are not so many of them. And also, it keeps my code for the callers cleaner, because the callers don't deal with this. The caller just say, for this game state, do something, and then the behavior kind of makes the dispatch and then makes the kind of the unhappy path visible, because once the game is over, then the game is over, right? And I sort of anticipated then the caller which deals with this understands whether the game is over or not, and will not call methods like go and take on the game state object, which with the game being finished, because the callers are kind of the outer business logic. So in my head, that design is sort of better. But as I'm saying, like, it's a little bit in the eye of the beholder, and it is sort of up to the designer to either push it down or keep it a little bit up, or like where you do the dispatch. I know it's a little bit hard, but if you try to implement it this way, you will know what I mean. It will impact the way the callers handle game state, right? There is a question. Yeah, that's right. So we do have some coupling. So we can do this, and Nick is suggesting that that introduces sort of some coupling somewhere, if I understand it correctly. So yes, it is basically a balancing game. Like, what do we want to couple and what we don't want to couple, right? So as I was saying here, you can do it this way, but then you're coupling two things together and it feels smelly, like it feels wrong, because this is in a different level to this, because it applies to different like levels of abstraction, right? When we have game over, we don't have inventory and stuff anymore. So coupling it on this level kind of breaks the boundaries. And it's the same here. if we do certain things like one way or the other, we kind of have to either be aware of something somewhere where we should not be aware of it, right? Or do it the other way around. So this one is quite interesting to study, and you kind of need to have a reason to do it one way or the other. Like why? Like what would make the code simpler and what would make the code more convoluted, and what at which level the decisions have to be done. And I feel it's a little bit, the designs could be different. Maybe this design would work better, but then you would have to do certain things on the coding side. All right, so the next thing that I wanted to talk about is the finishing of the state. And this comes surprisingly often in Rust because of the borrow checker. And one student kind of identified this and had a very nice solution. So here we have to do two things, and we have to deal with the state to check if the user has the win condition, and then if it has, we have to kind of finish the game. Like we have to change the state, right? But doing this kind of grabs the handle of the state, and then you cannot access the state in mutable way twice in two different kind of access points. So the way the student solved it is it sort of encapsulated the first access to state in a way where the mutable access is dropped after this bracket, and then we can get the state again in mutable way and change the state, right? So this is a kind of a Rust induced way of dealing with mutable borrow checker and mutable state access, because like we have to. And students usually deal with this in different ways, and some couldn't do it. And sometimes you are trying to this is the cleanest way to deal with this, basically scoping. So this kind of a scoping of access in Rust is very common. It's very common way of dealing with this. In this particular case, that's it's a very elegant way to deal with this. If you're starting with Rust, often it's tempting to make copies and make sort of multiple versions of something, because you have to avoid the double mutable access to something. So every time you're making a copy or like dealing with the move semantics or with copy semantics, you have to ask yourself, is there a simpler way? Maybe I can do scope and deal with this kind of by scoping my access, because then it's more idiomatic in Rust. Sometimes, yes, sometimes you do have to make copies, but more often than not, it boils down to doing some sort of pattern matching and some scoping tricks in Rust. So you basically have to find it. It's quite unique to Rust. Like you don't think about borrow checker in C++, and you don't think about borrow checker in Haskell or any other language. It's very unique to Rust, and it's very Rust idiomatic to deal with this using the scoping, using the scope. So this is, I just wanted to highlight that this is a nice solution to the mutual, like you have to access state twice, both times in a mutable way. You could say, do you really need to have a mutable state to check if the user has a particular inventory, right? Do I really need to have a mutable access here? And then you may say, maybe I don't. Maybe I just need read-only access, and I have I have two accessor methods, one which returns me a state in a mutable form, and one which returns me the state in read-only way, and then I just check stuff, right? And that would be fair. You could say, yep, that's fair for solving this particular case. You could update the API and say, on a game state, I'm introducing the extra accessor, which gives me access to state in a read-only fashion. But then you have to ask yourself, is it worth it? Like how much work that would be? Because the game state has all those extra, struct like fields, and I have to make sure that I don't allow state manipulation anywhere. And then you basically have to implement it, right? So is that solving only that single problem? And if the solution is longer than this solution, maybe this solution is better. If that read-only access to state would solve other problems as well and makes code cleaner, then maybe you can go with the other one, right? So again, there is no single perfect solution. Yeah, with the current API, and if, for example, you're making the game on top of the game engine where you cannot modify the API yourself, then this solution is perfect. If you're working on your own game engine with the ability to update the game engine API, maybe introducing read-only access to state would solve this in similar way, right? So again, it's a little bit up to you. It's a little bit up to the particular case. Okay, so I think we have two more to go. So typed outcomes. What it means is that we want to observe what the different functions return and why they return what they return, such that we can take advantage of it, right? So the game logic returns the types, and then the rendering module takes the types and convert them to text. So the business logic of the game.rs, that module does not deal with strings. It does not deal with the conversion. Like it deals with types and type matching, and that all the types are kind of correct. And the way we kind of present it and deal with the user is done somewhere else. So the logic is purely based on types, and it has influence of how we deal with tests and how we deal with the implementations. Because we isolated them. We isolated the rendering logic and the business logic. The business logic is not concerned with texts. The business logic is only concerned with the types, right? With the way the types kind of align, and like the constraints are expressed by the relationship of types. So a good test, which tests the business logic, looks like this, right? So we are in the hollow cave. We want to go west, and then we check if going west is blocked. Yes, it is, because there is a river from our cave to go west, and whether the current area after we try to move is the same. So we didn't move, right? So note that here we express the behavior without accessing any strings or accessing any rendering or any actual user interaction. It's all based on types. It's all based type checking, like what is the type of something that we got somewhere, right? And what is the instance, what is the variant of a particular type, right? So area hollow cave is the variant of the area enum, and then we basically checking things based on type checking, right? So this is a good test. And then we have this test. So we are checking if going west from the goal gives us the rendered action results, which is the output, and then the output contains this, right? Which option do you think you should so the assert And it says we should use assert equality. And that is kind of true. We should compare what we get with what we expect, because then the error message is more meaningful. Like with this particular one, it will just say it failed, but it will not really show us why. If we use this one, we have the comparison and it will tell us what the difference is. It's more meaningful. So B is not bad in a sense that, yes, we probably should use assert equality in that particular line. But the really correct answer is this one, because the game logic is correct, but what might have changed is the way we render it. Like, what if we render it in Norwegian, right? We have now introduced like a cross-language thing, and then we are rendering it in Norwegian, and the test will fail because this text is in Norwegian, right? So the test does not test the game logic anymore. The test tests the renderer. And then for testing renderer in isolation, we should mock this. We should not be testing game logic and renderer at the same time. Then it's not unit testing. It's kind of more integration tests, right? So when you're writing unit tests, you have to think, what is that I'm testing? And if you are testing logic, then your test looks like this, right? And then if you're testing renderer, you should be really testing renderer, not mixing game logic with the renderer and in some obscure way. Then you should do a proper renderer test. This one mixes two things. It pretends to be testing the game logic by testing the output, but it's wrong because the output may change and the game logic is still correct, and the test will fail only because the renderer has changed. So you should avoid that. All right, so then error propagation. We have, like, if we look at the take and go. So again, if we go to go, we say, yeah, we returning game result. And then if we go to take, we also returning game result. And why is that? Why we all of them kind of return a game result? Well, it kind of boils down to our happy and unhappy paths and the way we want to deal with errors and the way we want to deal with the unhappy path in our code. So we basically checking things and then returning if the game is over. So it's our guard. So we're doing our usual guard up front. And then we returning a particular errors up the chain. If we, for example, like we trying to take something from the area in the current position, but this item is not there, right? So this item is not in the area that we want to take it from. So then we say item is not here. And again, we're using a very nice typed errors such that we enforce handling errors and type errors. So the compiler is our friend, right? Again, we're using the compiler and the type system in our advantage. And then what we are doing here is, let me check. So we have to check if the let me see. So yeah, we are doing this unwrap, right? So we kind of unwrapping all the areas items, and this one will throw a runtime exception if something is wrong, and then this one is explicitly checking if we didn't find the item in the area. So here we kind of made an improvement because we don't want to throw a panic without telling the user or like the developer what went wrong. And this panic is basically because something was not initialized properly, right? So it is a developer's problem. It's not a state that should happen in the system really. So it's like a very edge case. But even if it is an edge case, we want to always use expect rather than unwrap, right? Every time I see unwrap in your code, that raises like red flags. It's like, okay, something is really smelly here, like something is wrong. This one also raises red flags, but it basically says, look, that should never happen. All areas must be initialized in the construction of the game. So if something is not initialized, we have really serious problem somewhere. Like that should never happen, right? And I know why it should never happen because I have this expectation here. So then instead of doing, instead of doing this none, I have a match, and then I'm checking if I got none, and then if I got something, then I have the unwrapping of the of what we are matching, right? So this is more verbose, and this one is uh, like this can be none, but I'm doing kind of an explicit check if this is none, right? Here I don't have the explicit check. I'm doing this sort of more of a happy and unhappy path, and I have um, the matching done in such a way that the unhappy path is sort of handled by the none case, and then the happy path gets me the result, which then I kind of use later, right? So if you sort of see this like what it kind of feels like I'm doing more code here than in here, but there is a certain like a spillover. The spillover is that I have pause, um, and the pause is hanging here, and it can be none. And then the pause, I have to do this unwrap, and the only guard before I am kind of binding this to this line of code is this check, right? And there were people who forgot about the return, for example, and they have this as an expression, and they were thinking that those three lines will return an error, but there was a typo, like there was a missing return, which sneaked in, and then because this could be none, then this one will panic, right? So it feels easier, but it's less secure. Like it leads to possible problems later on if something bad happens. Whereas this one is just a little bit more extra, it's like one extra line which explicitly deals with some, and this will never be bound to anything. And then this one, like if I forget this return, if I treat this as an expression now, the compiler will complain. The compiler will complain that this pause is not properly bound. Like one more time. This one can happen always. This will happen, and if I have a bug here, like I will have a bug, and then this one will throw and will be a runtime exception, which the compiler cannot help me with, right? So if I forget this return, the compiler will say, yeah, okay, there is some expression here, like, okay, whatever, and the compiler will let it fly. It will let it go to this line. But if I do it this way, the compiler, if I forget the return now, I have the same bug as before. But this time the compiler catches it, right? The difference is that my code, again, takes advantage of the compiler checking if I'm making bugs or making mistakes. This code does not. So this code may feel, okay, it's one line shorter, it's better. No, it's not, because you're not taking advantage of the compiler. This code takes advantage of the compiler, is one line longer, but if I have the same bug now, if I treat this as an expression, then this will not match. This, like, it will not work because the type expectations will not match. So the compiler will complain, right? So the explicit match is sort of already better than the if approach, right? But then you can do even better. You can use this. So every time you're using unwrap, it's a red flag. Every time you're using this thing, it's a green flag. It's like, okay, something is probably great. Somebody thought through the logic and came up with the idea of using this guy, using this question mark. So that is the best, almost always, right? So what this one does, it is again same as this one, right? We have this kind of expectation, which we decided to have because we want to make this a really developer problem. But then the rest is sort of following very nice idiomatic Rust pattern, which says, okay, we need to get the position. We need to iterate over all the areas, all the area items, and get the position which matches our item. But if we didn't find anyone, then we have this okay or. And this okay or basically says, okay, if at this point we have none, then we have to throw. And we gonna return this one. And then we basically saying, is this one really working? Is it okay? Or is this one not? And if this one is not, this error gets propagated automatically to the return of our function. So we get like remove the return. Now I cannot make my bug anymore because my bug was forgetting the return. And here I get rid of it. Like there is no return anymore. I basically have this one instead, right? If I forget this one, the compiler will complain. If I have this one, then I cannot make the bug anymore. Like this construction works to prevent me having a bug, the one which those two have, right? This one is the weakest one. This one is improvement, but not a proper idiomatic Rust neither. And the best idiomatic Rust is this one, right? I know it's a little bit harder to kind of think this way. And it's much more natural to think this way if you're coming from C or C++ or Golang. Like this code comes natural, but this code is smelly. This code is not Rust. This code is C or C++ or Golang. And this code does not take advantage of the compiler. This code is the idiomatic Rust. This one is like intermediate. This one is the best. It is like idiomatic Rust, takes advantage of all the Rust power and takes advantage of the compiler. And it kind of removes this ability for us to make the bug. And I kid you not, there were people who were having this bug in the task 16. They forgot the return. They basically were trying to return this as an expression, but it was kind of not working because they were in a place of the code which that would not be returned upstream up to here. The code will continue. So the compiler will not catch it, but they would have the logic error. All right, so basically this one is a sugar, like it's like syntactic sugar for something that uses monadic constructs that we learned about from Haskell. And it sort of uses this shortcutting, the unhappy path to shortcut directly to here. So this one basically says, okay, are we in the unhappy path? If we are, just stop here, right? And this unhappy path is expressed by this statement here. So if everything is okay, we fine. We basically get the position. But if we are not okay, then there is this or, and then we are basically in the unhappy path. So it desugars it into this longer, verbose kind of code snippet. All right. So Let me check. Yeah, right. So again, this is taken from the code that people wrote, and they were basically doing this unwrap thing. Try to avoid it. I'm not saying expect is to be avoided. I would say expect is fine, because if the developers did not initialize something for the game, that is our problem. Like that needs to be caught and fixed. So using expect here is fine. But you should never use unwrap. Every time you're using unwrap, you probably should replace it with expect. Um, so then we're doing this sort of pattern matching with the let, and we have code like this, which will work. It's okay, but this okay or is much more idiomatic. And this one is a little bit more tidy, a little bit easier to read, and it has this fantastic sugar, right? We should use that. We should use that every time where we can, because that makes everything else follow a certain pattern, which usually is an improvement, right? Um, so which code do you like more? Which code did you wrote? Did you write this one or this one? If you wrote this code, fine, it will work. Just replace this one with expect, and it's okay. But if you want to improve, yes, try to write code like this. That will be better. Okay. So this one is again an example from a submission. It's for dropping an item. And then basically what is happening here is that we using we basically dropping like so we let me see. So we have our usual guard, and then we have the second pattern, because we have to get where do we have this item, right? We need to get the index from the inventory, which points to the area that we have, like the index place where we have the item. And then we are basically saying we are removing that index from the inventory, right? And then we're saying, yeah, we drop the item into the um, from the inventory, but we forgot to add it to the game. So this one compiles, this one runs, and it kind of like we say we are dropping item, like we're dropping an axe here. The axe goes off the inventory, but it was not added into the area, right? It's like a logic error. We like the compiler didn't caught our logic error here, right? So it's a silent bug where we are not adding the item to the area where we dropping it into. So if you're reading code like this, would you catch this bug? Would you identify that this is the silent bug? If not, then you need to practice a little bit, like doing kind of a reading like I did, like what is happening here, what is happening here, and then what is missing, right? I kind of like, of course, I prepared the slides, but I kind of forgot exactly what the bug was. So I had to like comprehend the code one more time. And the hint is here. So the work was not that hard, but doing kind of a reading of the code and analyzing it and kind of understanding what is not working is something that you will have to do in the exam. And do a little bit of a study of the task 16, because task 16 is an oblique. So everybody is expected to be able to do something with task 16. So code like this might be in the exam. Okay, so then the test drop place item in current area is marked as ignored, and that basically is silently ignored. That's why it's a silent bug, because the code is wrong and the test is ignored and does not catch it, right? Okay, so then we have couple of approaches to go. We have this one, which basically follows sort of like a table, right? So it's like table driven means we have code which sort of looks like a lookup table, right? And the lookup table basically is here, and then we have explicitly handled like what we don't have to handle in the table, because we like if we are here, we basically saying yes, there is we are kind of at the edge and we are not handling it, right? Like we just shortcut it like with this error. um, so this table, like should we fix this code smell, like to remove this ability for us to make this? Yeah, maybe, but it's not the point here. The point is this, and it's kind of nice, right? So then we have a single match. So here we have like a little bit more convoluted matching, because we are isolating the error case. We're doing the main logic with this thing, and then we're doing some auxiliary things. Here we have this total match, but we have to repeat a common logic. So, like for example, if we have to go through mountains, it's very similar to doing the thing with the river. It's just that we have to have a different item, right? So we would have to kind of repeat this logic inside here, right? So here we shortcutted it into that. So instead of repeating the logic, we basically took advantage of this struct of this construct, and we basically are checking, can I go there if I have that item that is required for us to do it, right? So we have a table, and then we combine the business logic into a single it's like the same discussion as we had before with the arms. We can have four or two different functions. Here we just have one, right? And this is just this one place, one logic. We do a little bit of preparatory work of what is needed, that for mountains we need a rope, for river we need a canoe, but the logic is common. It's the same logic. We don't copy and paste it. Here we have to copy and paste it, right? Because here we're doing it for canoe, and then here we're doing it the same logic as this one, but with the rope. Cold smell. You should avoid this. So yes, this will work, but you have a really big chunk of code. This chunk of code repeated twice, just with the different item, right? You should refactor it, and you should sort of try to do it this way, like table way, and then have a logic in a single place, right? And then we have the if chain. Yeah, uh, the most ugly, and also does not check for exhaustive check. Like the compiler is not your friend anymore. The compiler doesn't know what you're doing. Here, the compiler is your friend because the compiler will complain to you if you didn't match something, right? The compiler will say, wait a minute, you forgot about something. You forgot about ocean. Here the same. The compiler will complain to you because we are taking the advantage of the match, right? Here there is no match. The compiler doesn't know what you're checking, and the compiler cannot help you with the exhaustive check. So every time you having kind of a if chain, or every time you sort of really doing if, you have to ask yourself, do I really need that if, right? Most of our refactoring so far, we're getting rid of the if. Like here we did the same, right? We had the if, here we have no if, and it's better, right? So every time you're doing if, you kind of should scratch your head and say, do I need the if? Yes, we do have the if, because we do have some cases where, we can just go. So for this case, there is no item. And because there is no item, we don't have to check. if we contain something, right? We just move the player, right? If there is like none, this if is not avoidable, it's desirable and it's fine. But those ifs are kind of undesirable. Like you should really replace them with this. Oh, sorry, with this. Okay. So, expressionless statement. Oh yeah. So this is something I was talking about. There is a missing return. And this is treated as an expression. The compiler will work and this code will continue to execute. And that may lead to a runtime panic. So that's kind of a bug, right? So those bugs you should avoid. You should kind of look at the and hopefully you can avoid them by making them irrelevant, right? Like actually making them impossible. This particular case, this bug is possible. Yeah, what this line of code returns? It returns the error from the function immediately. It constructs the error value, then immediately discards it because it's not used anywhere, right? Option B. For this one, it's option B. Okay, so the last topic. The last topic is, again, from the submission. We have code like this. So the player has dropped axe in the flooded grove, and then the area item's flooded grove is currently axe, right? So, that is, it should be, it dropped canoe. So the player is dropping canoe in the flooded grove, and currently the flooded grove is just axe, right? It's a typo. This should be canoe. So then we basically putting canoe into the vector, and yeah, just read the code. Read the code and tell me what will be the area items in flooded grove after the code runs. Will be A or B. So currently, sorry. Yeah, we are dropping the canoe, and currently it's an X. Yeah. So A or B. I will change this. So this is, I will just, let me see. I will quickly fix this. Is dropped canoe. Canoe, yes. All right, so that's this. Like, okay, what was this slide? This is slide number 50. Okay, so 50. Yeah, so we already have canoe. Perfect. So then what's the answer? The intention is to drop the canoe in the flooded groove. The flooded groove currently has axe. You wrote the code like this. Anyone? Yes, we have someone answering. Carolina says B. Yes, correct. There is another answer. Yes, you're replacing the map. Exactly. So the answer is B, which means we lost the axe, right? Originally, flooded groove had an axe, and now we sort of lost it, right? Because we inserted um, a new list, new vector, which only has the canoe. We forgot about the original vector which was there, right? So the insert is not the right thing to do. Insert is not the thing that kind of works here. So how about yeah, so setup, the original is still X. And now instead of doing the insert like we did here, we're doing that. So what will be the answer now? Will this code compile? Is this code correct? It says here correct implementation. So it is just a sanity check if I didn't make a mistake. Is this code really correct? So yes, and the answer A, yes. So I believe this code is correct. We're basically getting the current list, right? And again, we're throwing here if we are trying to get a mutable area list for the flooded groove, and it gives us nothing, right? It gives us none. Then we like, okay, we kind of don't initialize it properly. Like we are getting something from our hash table, and if our hash table does not give us an empty list or empty vector, that means we did not properly initialize it. We should throw. The developers did something wrong. Our game setup is wrong, right? So again, expect here is kind of okay. And then we basically get the vector which we can push canoe into it, right? So if the vector originally had an x, then we pushed canoe into it and now it's fine, right? So this implementation works. So this is this kind of insert versus get mutable and then push, right? So the insert basically replaces the key with whatever new thing we want. And then if we get mutable and push, then we basically get the old thing and push something to it. So we get this preserved, right? There is this additional thing. Which we can use as well. So we can say we want the entry for the key, and then if everything is okay, we push. But if something is not okay, we say or, and then we initialize it with the empty vector, and then we push, right? So the current implementation kind of throws, which again I said it's fair enough. Like we probably indicate to ourselves that we did not properly initialize stuff. But if we want to initialize stuff lazily, we can use this construct instead. And then we say or insert with, and then we can say new vector, which is empty, and that will be kind of initialized for us on the fly lazily, and then we have the push on top, right? So if we want like to avoid this expect, which again is a little bit problematic potentially, we can say, yeah, we don't initialize everything up front. We initialize everything on the fly lazily and then have this one, right? So then you have to remember this or insert with construct. Okay. Okay, so here there is a question again. So what happens if we do this? And if the playing state did not pre-populated all the areas with the empty lists, what's gonna happen? Well, what's gonna happen is this one will panic, right? You will have a runtime exception, right? This one does not insert any new empty vectors, right? It does not, but if you want that behavior, you can do this. Okay, so any questions for the current material? What I will do is I will put the slides, and I have slides with notes which actually explain what I was explaining. So I'll put slides with notes onto the wiki, so people who are studying and who missed the lecture can read on the explanations as well.